Don't? It's not up to me. All right. This week's education topic is reversing and binary exploitation with Jacob Dahl. Everybody clap it up.
I'll put that in my pocket. Hello. Hi, thanks. Wow, all right. So yeah, like you said, when we're talking about reversing and binary exploitation, this should be fun. If any of you showed up to my interest group for reversing, these slides are gonna look kind of similar. So let's get this going. We good? All right, cool. All right, so let's go a little bit into reversing. So reversing stands for reverse engineering, AKA it's the idea of figuring out how things work. This can be applied to literally anything. Typically when we talk about reversing though, we're talking about reversing a program, trying to figure out how it works. But I've seen this work with like reversing internet protocols. Let's say you have like a piece of malware that's communicating with the back server and you need to figure out how it's working. That's kind of considered reversing as well. But yeah, get ready for some assembly. I know some of you that might be in 201 right now, you're about to hate this, but don't worry, it is fun. All right, so why should you care about reversing? So as I kind of already touched on, malware analysis is a big thing with reversing. So trying to think of some notable examples. WannaCry ransomware was actually reversed by some dude, and he was able to stop the ransomware basically from infecting more machines by discovering it was pinging some domain, and he just bought the domain and it stopped. Discover trade secrets. You'll see this a lot within like government organizations or even just like corporate espionage too. Maybe not one of the better ones to do, but like, you know, if you're trying to make a quick buck. We also do this to find vulnerabilities in like non-open source code. So let's say we're talking like proprietary applications. The first one I can think of is Zoom. That one has been analyzed by other people as well. We also have binary patching. Let's say you have a binary that just doesn't work and you know exactly where it needs to be fixed. You can just patch it. And you know, maybe you're just psychotic and you want to do stuff for fun. You don't like yourself and you just love assembly. All right, so where do we begin when we're doing reversing? So typically, as I said, when we're doing with like programs, we have the idea of two different analysis points. We have static analysis and dynamic analysis. Static analysis is essentially where you analyze the file without running it. So purely on the hard drive, we are not quote unquote double clicking it or running it at all. First, you'll probably start off by looking for strings within the file, look at header information, metadata, etc. Some useful tools that you'll use here is like strings. If you're dealing with like Windows binaries, PE view will show you all the header information from a PE file. Elf dump does the exact same thing, but on Linux. You also, in this step, will disassemble the file, which is just, you know, seeing how the program actually like runs. You can even quote unquote decompile the file, but that's kind of frowned upon within the community. We'll touch on that a little bit later. And sometimes you even have access to the source code. So like if we're dealing with JavaScript, you can obfuscate it, and then you will go through and try and de-obfuscate it. And sometimes even with Java, if you decompile Java, you can get the raw source code. Just all the variables will be different names. And then that leads us into dynamic analysis, where this is the somewhat fun part where you actually run the program and you see what happens. Hopefully you're doing this in a VM or a sandbox, unless you're like really ballsy and you don't care about getting malware on your machine. Hopefully you're not doing that, though I have known some people to do that. They're kind of dumb. All right, so let's get into some terminology that I'll be using here. When I'm talking about a binary, I'm typically talking about a binary executable. You know, like I said, a file that you can double click. We have this idea of high-level languages. These are languages that make it easier for you to understand what's going on. Things like C, C++, Rust, Go. Sometimes people even put interpreted languages like Python or Java in there, but for the topic of this conversation, I'm going to focus mostly on like C. Then we have assembly language, which is what your high-level languages are compiled into. It's human-readable machine code. It's almost a one-to-one translation to machine code, and the syntax is completely dependent on your CPU architecture. Some of you may know like x86, MIPS if you're really old or you do stuff with routers, and ARM if you like Macs. Machine code is basically what the CPU reads, a bunch of zeros and ones. Sometimes you'll see this in hex as well. But yeah, we'll continue on. So some more terminology. Disassembly and disassemblers, they're basically taking that machine code, that integer representation, and turning it into readable assembly language. Apps that you typically use for this are like Ghidra, IDA Pro, Radare. Some people call it Radar. I don't agree with that. We also have decompilation and decompilers. This is translating machine code into a high-level language. Typically, this is C. I have seen it done for Go, but it's really hard to do it for Go. Some example apps that do that, again, Ghidra also is a decompiler. IDA, if you pay for it, has a decompiler. Or, you know, if you're a little sneaky and you have a paid version for free. And then Cutter, which is technically the GUI version of Radare, has a Ghidra plugin that allows you to decompile it. And then finally, we have a debugger, which is what we use to run a program and interact with the machine state. We generally use the debugger during dynamic analysis. Allows us to set breakpoints, examine memory, adjust register values. You know, I know when most of you program, you just use print statements, but you know, sometimes a debugger comes in handy. So for like Windows, you'll see people use WinDebug, OllyDebug, or x64 debug, and then on Linux, you'll see like GDB and Pwn debug. Fortunately, I'm not too familiar with Mac OS, so I don't know much tools for like debugging there. Ask a manual if you want to know. All right. Now we start getting onto the fun stuff. Now we're out of the terminology. So assembly is fun, but where do we start? So whenever you have a program written in C or some high-level language like that, first it has to get assembled into assembly and then compiled into your machine code. So if you kind of see this diagram here, they can't see my mouse. All right, well, it's kind of like a tiered system. So high-level language is assembled into assembly language, which is then compiled into machine language, which is then interpreted by your CPU. Typically, when we are disassembling or reversing, we are taking the machine code and turning it into assembly, as I've said before. Sometimes we'll try and convert it into a high-level language like C. Actually, I'm going to go back to here real quick. Generally, what I was saying earlier, we don't do decompiling a whole lot because it's not always a one-to-one mapping because we're using something called signatures, and it doesn't always translate well from machine code. So typically when we're going to be reversing, we're going to be looking more at the disassembly because it is a one-to-one mapping. So finally, the real fun, assembly. Yeah, lots of fun. I remember first time looking at assembly and I was like, what is this? I don't ever want to do this ever again. And then I turned into a bit of a masochist and wrote a program in assembly, which was not fun. But it's a great learning experience. So the first thing you're probably going to look at when you see assembly is this idea of registers. You don't have like variables in assembly. You can really only move memory or move data from one location to another or operate on that data. Therefore, you have to be able to store that data in something very small so that it can be operated on. We use registers for that. So here on this slide, you'll see probably the most common registers that you'll use. EAX, EBX, ECX, and EDX are used to store like variables, quote unquote, like store data so that you can operate on it. ESI and EDI are used when you're like looping and trying to copy data from one location to another. This is typically used when you're using like a mem copy in C. This is a great example. Then we also have your stack pointer and base pointer. I will talk about that a bit later, but those are also very important. Another register that's not listed here is the instruction pointer, which essentially just is a register that stores the next address, or the address of the next instruction that will be executed. So I kind of talked about this. So operations. On x86, there are 1,503 of them. which is a lot. But typically speaking, you're going to really be using like these 6. There's like some really niche operations that x86 added that aren't necessarily needed. Why? Sorry, I got a question. Yeah.
Yeah. Isn't it true that you can just use one of them, just MLB? Isn't MLB Turing complete?
I think so, but like if you want to like do like mathematical operations, like anything with the ALU, you have to use like add, sub.
Okay, so Howard instructions.
Yeah. I guess if you want to, if you live under the impression that everything can be done at compile time, then yes, I guess you could write a program that's completely just written with move statements. But unfortunately, I can't think of any programs that doesn't have some form of dynamic state. So we do have to use these other operations. So you like we were kind of talking about. So we have these 6 common, or like what I like to call common. So you have the mov, add, sub, mul, div, and LEA. So the first instruction is typically used to move data in and or out of a register. You'll use this to store data inside a register. You'll even be able to use this to pull memory into, like a value that's stored in memory into a register. You can even use it to store a value that's stored in a register into memory. Then we have add. That's pretty self-explanatory. Just adds 2 registers together and then stores it in the first one. We have sub, which is the exact same thing, where it takes the first register and subtracts the second register and stores it in the first. Mul and div, also kind of self-explanatory. They multiply 2 registers together, and div divides the 2 registers. And then the fun one is LEA, which loads the address of something in memory to a register. LEA stands for load effective address. You'll typically use this when you're trying to pull like a pointer to something on maybe even the stack or just in memory in general. But I'll touch on that a little bit later. You can see I kind of did a little bit of an example here on the bottom of the slide. I'm putting 9 into the register EAX, and then I'm putting 16 into the register EBX, and then I'm adding the 2 together. So then after this program runs, EAX will hold 25, assuming that I can do math. Yes, cool. All right, so registers are the smallest form of memory in assembly. But unfortunately, I don't know about you, but I don't think I've ever had a program where something only takes up 32 bits of address space, or 64 if you're using a 64-bit. So that's kind of where memory comes into play. We use memory to store large portions of data and even just what we're executing in general. So whenever we have a program, so a program is what is called when it's still on the hard drive. A process is what the program is called when it's loaded into memory. So when we load a process into memory, we have this idea of these segments of memory. So we have the stack, which is where you're typically going to hold like local variables. The heap, which is where we're going to hold dynamic memory. We have uninitialized data and initialized data, which are used to store like global variables. Whenever you are working in C, if you mark something as static, it's going to be stored in the data section. And then the text section is where the actual executable code is stored. So when we were talking earlier about how machine code is just all stored as text or stored as data, like integers, that is going to be stored in the text section of the process. But yeah. So I kind of touched on it. So the stack. So the stack stores a lot of useful information. We use the stack a lot. Without the stack, you would not be able to run a program. You would not even be able to have functions, really, within a program. The most useful information, or most pertinent information you're going to see with the stack is the address to actually return to whenever the function is done. All of your local variables for the function are going to be stored on the stack. And depending on your ABI, parameters that are passed into the function are also going to be stored on the stack. One thing to remember is that the stack grows down the address space. So you will start at a high address, and with the stack, as it grows, your address of the stack pointer is actually going to decrease. And that's useful for whenever you want to access your local variables. So I kind of talked about this earlier, about how there's 2 registers that we use and for the stack, and that's ESP and EBP. ESP is called the stack pointer. It represents the top of the stack, which is kind of a weird way to say it because that's actually going to store an address that is lower than your base pointer, which stands for the bottom or the base of the local stack. So if you kind of look at this diagram that I have here, this is representing a function that takes in 3 variables and has 4 local variables. So you can see here that EBP is our base pointer, and to enable to access the local variable, we are going to access that via the EBP register. So for instance, if I want to move the value that's stored in XX into a register, I would have to reference EBP -4. But if I wanted to refer to one of the parameters, I would use EBP +8. Like I said, these registers are really useful for just accessing data on the stack. That kind of leads into the heap. Programs are unpredictable. We don't always know how much memory we need. So we have this idea of dynamically allocating memory at runtime. And unlike the stack, the heap actually grows up the address space. So you'll start at a low address point in your process, and you'll grow up. As I said here, or as you can see here by the Veeam, you have to actually, as a programmer, allocate that memory and deallocate that memory. A lot of people forget about that second part, and that will lead into some weird binary exploits that we're going to touch on a little bit later. Definitely look for these functions when you're disassembling, because I can tell you that, especially from personal experience, that you don't always free all the memory you have, and you'll have things like called memory leaks. All right, program flow. This is what actually allows you to run your program. If you don't have these, like, quote-unquote if-else statements, your program's just going to run linearly. It's just going to move one instruction to a next and keep going until it has no more instructions to run. But that's not how programs work. We have this, we do have, like, state that we have to check for. So we have this idea of, like, if-else statements in high-level languages, but in assembly, it's considered jumping and comparing. So you can jump to a new area in memory. This is also called branching. If you are ever using IDA or Ghidra, you can actually look at, like, a flow graph that will show you the branch flow of the assembly program. Jumping will change the EIP register. So like I said, the EIP or RIP register, if you're on 64-bit, it stands for the instruction pointer, and it basically points to a location in memory that contains the next instruction to run. Normally, like I said, EIP will just increment by 1, but when you're jumping, it will actually increment to whatever the location is that you want to jump. There's several ways to jump. You can either use the call operation in assembly, or you can just use the JMP instruction in assembly. I will give an example of an if statement here. So you can see the program on the left. It's just a simple program. It just takes, puts a variable that stores 9, checks if that variable is less than 11. If it's less than 11, it's going to return 0. Or else it's going to return 1. Now, on the right, you're going to see the assembly output of that. The colors are kind of aligned with what the instruction gets compiled into or assembled into assembly. So you can see that line 2 in the C program is directly comparable to line 4 on the assembly program. But the thing I really want you to look at is lines 5 and 6 in the assembly. You can see that we're comparing the local variable, which is RBP -4, and we're comparing that to 10. And the JG assembly operation stands for jump if greater. So essentially, if the comparison between 9 and 10, if 9 is greater than 10, we're going to jump to the location in memory, which is marked as L2. Or else, we're just going to continue, put 0 into EAX, and then jump to the end of the program. One thing I will touch on here, I think I forgot to talk about, EAX, whenever you're dealing with function, typically stores the return value of your program. So whenever you're disassembling a file, you will see before the very end, you might see a move operation in EAX, and that's going to be the return value of the program. But yeah, this is basically the assembly output of a basic if-else statement. One thing you can also see here is that, you know, it's not always a one-to-one too. My assembly or my C program has 8 lines, and my assembly has 13. And that grows exponentially. You could have like a C program that's only like 30, 40 lines, and that can translate into like 100 lines of assembly. It's not always a one-to-one. That's why decompilation is not always very feasible. All right. I'm also going to do a for loop, because essentially what a for loop is a repeated if statement. You could do the same logic with an if statement. You just have to write the if statement 15 times, which is just, I would never do that. Please don't. As a TA, don't do that. So yeah, here you can see it's a simple for loop. We're just adding I into A, and then we're returning A as the output. Like I said before, this is a 7-line program. It turns into a 16-line assembly program. You can see here on lines 5 and 6, that's where we are, we're jumping to L2 right after we put 0 into A, or sorry, 0 into I, which seems weird, except we're doing the comparison after the actual operations. So on line 12, you'll see that we're comparing I to the value 14, and if it's less than or equal to, that's what the JLE stands for on line 13. If it's less than or equal to, then we jump up to the location L3. So it's going to run iteratively, as I said before. If we don't have these comparison, the program just runs down the lines until it runs into a jump statement. And it's going to keep doing that until the value that is stored in I is no longer less than or equal to 14, at which point it jumps out of the for loop and we return. And like I said before, you can see on line 14 that the operation right before we return is moving the value that is stored in A into EAX, since we are returning the value. All right. So now that we have kind of some fundamentals into assembly, most of what you're going to do with reversing is just understanding assembly. So having a really deep fundamental understanding of assembly will allow you to be able to reverse the program and understand what it's doing. But how do we apply that understanding of our reversing? Like, how do we, like, if we're going to want to create a binary exploit, we're going to have to reverse the file and figure out what it's doing. So there's some key things that you want to look for when you're reversing, and I'm going to talk about that with these with binary exploitation. So what is binary exploitation? Essentially, it's just abusing flaws in software and make it do something it doesn't. Honestly, you could probably say that's all of CSEC. The CS department makes it, we break it. We love finding things that are not normal. When we're doing binary exploitation, we want to transition into a state that is unintended by the programmer. We will abuse whatever flaws or vulnerabilities that we see in the program and make it do something that the programmer did not consider. Vulnerabilities are contained within the class of bugs. So if we're going to talk about the difference between like a bug, a flaw, or a vulnerability, bugs will always exist in your code. It's up to you to figure them out. A flaw is something that has unintended behavior, and a vulnerability is something that will break the program. And then an exploit is using that vulnerability to get some form of gain, whether that's like monetary or just trying to break into the program for privilege escalation. There are so many examples of exploitations. So as I talked about earlier, like when we're reversing, we are looking for vulnerabilities. We're looking for an interesting area of code. Something that has messy logic, which when I was talking about earlier with all those branch statements, maybe someone has a switch case and they don't actually have a jump for every single case in that switch statement. Or maybe when they're jumping to a location in memory that may or may not exist because they may have deallocated that piece of memory by calling free. So we're looking for things like that. We're looking for a control path. that might lead to something that is unintended. We also look for areas of code that are historically, there's a lot of bugs. For instance, if you ever see like a piece of open source software, if there's a vulnerability that's found or like a CVE for that open source software, keep looking there. More than likely, if the like coder or programmer has put a bug in that location, they're going to have other bugs there too. You know, follow what you know. Don't always go off the normal path. And also look for like important pieces of like code. So for instance, anything that's going to be taking in user input, definitely look for that, because that's something that you have direct access to or control over. You know, after you find that interesting piece of code or that area that you want to look for, you have to analyze it. So that's kind of where we, again, talking about the reversing, understanding what that code does. This is a lot easier if you have the source code, but it's not impossible if you don't. We want to understand what the code's purpose and the results of that code. And then finally, after you're done analyzing the code, find a vulnerability. Find a good starting point. There's always just common issues. We have things called integer overflows, underflows. This is caused by, so when you have an integer, it can be either a signed or an unsigned integer. So let's say we're storing a signed integer and we go over the max value of that signed integer. So for instance, with a 32-bit number, the max signed value you can have is like 2,700 and something million. If you go over that value, it's going to return to like -1. So that would be an example of an integer overflow. Something that causes an array to go out of bounds. So for instance, whenever you have an array of size 15 and then you index like 16, that's not good, not allowed. Please don't do that. That's called a buffer overflow. If you are able to like exploit that fact, if you are able to go out of the bounds of the array, that would be called a buffer overflow. There's also this idea of heap overflows. I forgot to put that in here, which is the same thing as a buffer overflow, but on the heap. Generally, heap overflows are a lot harder to exploit because the location in memory is not always static. So we'll go a little bit more in depth with our quote-unquote attack vectors. So we got to find some piece of code to look at, to attack. Like I said before, you want to look for where many vulnerabilities have been discovered before. Like I said, it's unlikely that all vulnerabilities were fixed. Don't just assume that because someone says they fixed it, they actually fixed it. They could have just made it worse. That point I really want to talk about is programmers don't always code securely. I know a lot of people that don't care about security when they're coding. It's just whatever the quickest thing they can get done. And that's when you wind up with production code that breaks and then cause vulnerabilities. Find important to security code. So, you know, like drivers. We may not care as much about user space because we don't have privileges there. But if you can find a vulnerability in a driver, especially on like Windows, there's a very good chance you might have kernel level access to memory or other I/O devices that you can abuse. Sometimes programs sandbox components. If you can find a part of the program that isn't sandboxed, that would be great. This is typically more useful with like mobile applications. A lot of your mobile apps, especially on Android, are completely sandboxed from the get-go. But if you find that they're like writing to shared portions of the drive, you might be able to abuse something in that. And then yeah, finally, like find messy logic. If you find a function with a lot of if statements, they may have missed something. Like if they're trying to like make sure that there's no way they're doing like sanity check or they're cleaning their input, sanitizing it, they may have missed something. So like try and see if you can figure out that thing that they missed. Check if there's redundant checks. It might indicate that the programmer doesn't really understand what they're doing. You'll see this a lot when people are programming with legacy code bases. Lots of old code. Don't really want to learn that old code, so you just write whatever you can find. I guess a big point on that is make sure you read documentation, kids. If you don't, you will sometimes write the wrong stuff. All right, now into that next point, analyzing the code. So this is where I was talking about the reverse engineering comes in. Hopefully the code is open source. It's not always. If you're working on a proprietary tool and you work within that company, you will have access to the source code, but not always. It's a lot more fun than looking at assembly. You can see in the bottom right, that's actually the output of IDA. That's kind of where it's showing all the branch locations. All those lines represent a different branch that it can take from the control flow perspective. You want to figure out exactly what inputs you can control. If it's reading from a file and you have access to that file from like a read-write perspective, figure out if you can abuse that. If you are providing user input either from the command line or using like fgets or something, see if you can abuse that. You want to take over whatever access you can get. This step is very important, but often overlooked because people hate reading assembly. Yeah, no one likes assembly. And then, yeah, finally, find your vulnerability. After you've gone through that like main analysis point, start doing like manual review of that code. Maybe this code is relying on some open source driver. Look into that. Find common issues. I know I've gone onto GitHub before and just looked at the issue tracker. And if those issues haven't been resolved yet, there probably is going to be a bug there. If someone has an issue there, that means it's unintended behavior. We also have this idea of automatic reviewing of code. So fuzzing is where you have a program find the bugs for you. What it does is, let's say you have a program that takes in user input. What you're going to do is just continuously generate new user input until you wind up in a control path that is unintended. This is what the researchers did when they were looking for the sudo exploit. They were fuzzing the command line arguments that were passed into sudo. And they found out that if you passed in a value into sudo edit and then like -i and then 26 characters, it would cause a heap overflow, which is a really weird control path. And they did that after analyzing the source code of sudo and saying, hey, wait a minute, this looks weird. And then after they figured out all that, the researchers themselves did not discover an exploit, but then people found exploits. I forget exactly what version of sudo that was, but that was a very, very bad vulnerability to find. And sometimes there's even automatic static analysis. If you compile your program with WAL, sometimes like the programmers of like very big projects, they just don't do that because those warnings become errors and it won't compile. So if they don't want to look at errors, they just drop all the flags. Kind of that idea of if I don't know it, then it doesn't exist. That's a very bad idea. Don't do that. This is very time consuming. Fuzzing can take upwards of a couple hours, even a couple days if it has a lot of control inputs. Don't expect this to be right away. Actually, I can say about all of this, binary exploitation. This takes a lot of time. This is not something that you're just going to jump into. It's a quick 30-minute project. If you're going to do a lot of research, this takes a lot of time and effort. So touching on those like known vulnerabilities and those vulnerability classes, we group vulnerabilities into classes. Like I said before, we have buffer overflows. I'm going to actually give an example of a buffer overflow after this. I think after this slide, maybe two more. We have an integer overflow. It's generally not considered, like it's not a vulnerability in itself, but it leads to unintended results, which can lead to a vulnerability. We have uninitialized memory. So like if you have a variable, a local variable in a function, and you don't initialize that, that variable can be set to whatever. And that's undeterministic behavior. Printf, that's a big one. If you printf, like user input, they can do what's called like, I forget exactly what it's called, but they essentially what they do is they can do percent like %p or %s and pass it in as a user input, and it will just print values from the stack. You can actually use this to figure out what the size of the stack is, and this will lead into another exploit, like exploiting a buffer overflow. So if you're ever going to use printf and you're going to printf user input, make sure you sanitize it by calling %s and then the user input, never just printf the user input. That will just, bad idea. There are much more. Fortunately, this presentation, I don't have enough time to actually go into all of them, but There's a lot. Look into it if you're interested, or talk to me later. Yes, stack overflows. Gotta love them. This is caused by reading too much data to a buffer. So like, for example, if you have an array of size 50 bytes, and then you read 100 bytes to that, your program will attempt to store it in that array. And generally speaking, it will overwrite data if it is able to. If the stack is big enough, it will just overwrite values on the stack. Hopefully it doesn't get to that point. Generally speaking, your programs will segfault, but that doesn't always happen. And when that doesn't happen, that's bad. Functions that are famous for doing this, string copy, mem copy. Gets is a big one. Never use gets in your programs, kids. Very insecure. Even programs like fgets, though, too, and string and copy have exploits as well. Like, not even these memory safe functions can cause overflows as well. So, like, in order to exploit these functions, we have to be able to know what we can overwrite. All right, so now we're going to go into a basic example. So this is a very simple C program. It literally just gets user input by using the gets function, and it stores it into a char array of size 16. So if we're looking at this from the stack perspective and seeing what's going to be stored in the stack, if we look at the top of the stack, that's where the buffer is. Then we have the saved frame pointer, which is also the base pointer, or the stack pointer. Then we have the return address that our program will return to after it's done with all of its execution. And then the arguments that are passed into the main function. Unfortunately, I did not put those parameters in the main function. So how do we exploit this? We have to figure out what we can overwrite. We know that we can overwrite local variables, but the most important thing is you can overwrite the return address. So, like, what happens if we overwrite the return address to a function that gives us that can give us a shell? So, like, if we have shell code that is compiled code that you can supply as a user input. There's libraries that will allow you to be able to generate shell code that can, like, execute a bash shell, and then you have, if it's a program that has root privileges already, then now you have a bash shell with root privileges. This exploit doesn't generally work anymore because of some mitigations that I'll talk about later. But like 15 years ago, this was a very common exploit where people were using gets unsecurely, and then they were overwriting the stack address, or they were overwriting the return address and returning to their stack that the variable that they were returning to the data that they supplied to the stack. So kind of what I was talking about here, so what happens is we call it gets, but we supply, instead of supplying 16 bytes of information, we supply 28 bytes of information. So 16 bytes of that will be no ops, which basically are no operations. Then we have our shell code. Then we overwrite the local variables with shell code as more. And then finally, the return address gets overwritten. We return to the address of our shell code, which basically allows us to execute things on the stack. We don't want that. We don't want the user to be able to add binary info into our program and then be able to execute that binary info, which is why we have a lot of mitigations for that. That was, like I said, it was a big issue, and we no longer have that because of these mitigations. There's this idea of return-oriented programming. In our simple method, we just made use of one stack frame, and we were able to overwrite the other stack frames as well. So instead of overwriting one return address, we could overwrite multiple return addresses, and we're roughly overwriting the return addresses of, like, all of our previous stack frames. So if we were to supply more than 16 bytes of information, and even more than the size of our stack, we could overwrite more than just one function, because generally in the text section of our code, everything's stored compactly. There's not much space between functions. So what we started doing is randomizing the locations of memory, like the locations of where we were storing things in memory. the reason why this is important is the only way that you knew exactly where to return to on the stack was because the stack was always going to be at the exact same location every single time you ran the program. Now, when you run a program with ASLR, which stands for Address Space Layout Randomization, it randomizes the offsets of sections in memory. So your stack, heap, and even like the text sections are no longer stored at the exact same point in memory. All of this is determined at linking time, and it is one of the mitigations that you can use against inserting shellcode. There's still things that you can do to exploit even with ASLR. There's something called return to libc, but that is a very complex topic, and again, if you want to learn more about that, talk to me later. Yeah, like I said, the basic idea is that you can't return to something if you don't know where it is. Now we have DEP. This stands for Data Execution Prevention. With sections in memory, like I said earlier, there was a diagram that I showed where it was like the process in memory. There's like the different sections, stack, heap, text, data. What you can do is you can mark those sections as executable or non-executable. For instance, I can't think of any reasonable reason why we would need to be able to execute anything on the stack. So we mark the stack as non-executable. It will only ever store data. You can only ever read data to the stack, or read data from the stack, or store data to the stack. We're never going to be able to execute. This basically makes it impossible to execute shellcode on the stack. You're no longer. This is why most exploits nowadays you'll never see like shellcode injections because of this mitigation. Yeah. Also, fun thing, we have stack canaries. If you have ever heard about miners back in the day, what they would used to do is they would bring a canary in a cage to determine if there was a natural gas leak, because natural gas is very toxic. So we have this similar idea here where we have a stack canary. If we overflow the stack and the value that we store there is no longer the same, it will segfault. We put some random value at the start of the function, typically at the very bottom of the stack. So if we're thinking about how the stack grows down, we're looking at EBP like +1. We're going to store a stack canary. And if that gets overwritten, that means that we overflowed the stack and we cause a segfault. This basically breaks stack overflows. Not entirely, though, because there is a way that you can figure out the canary variable if you are smart enough. I personally have never done it. I just know there is a way to do it. I guess that's it. Yeah. Well, I thought there was one more slide. I think I might have accidentally deleted it. Well, either way, here's the resources. Any questions? So are you talking just reversing, or like binary exploitation as well?
I guess just reversing for now, but like
So for reversing, there's this website that I use. It's called crackmes.one. It's essentially just a giant repository of crackmes. You can search by like difficulty. It's user submitted files, so take them with a grain of salt. Don't like run them on your computer. You have no idea whether you're going to download like malware on your computer. But these crackmes are like generally programs where it's like, hey, figure out what this does, or hey, figure out what the flag is, figure out what the password is. There's a lot of beginner ones. I use that to learn a lot of stuff. As you start getting upwards into like the harder ones, you're going to have to start using a debugger or even implement patching. Just to get the flag. It's kind of like a CTF, but like minus the CTF portion, I guess, if that makes sense. So like you're given a binary file, you have to figure out what it does, and generally, quote unquote, the flag is the password that unlocks the file. As for binary exploitation, I guess the biggest one I can think of is mostly your beginner CTFs. The first one that comes to mind is Pico or Pico CTF. I know there's a lot of really good binary exploitation like challenges there. They generally archive all of their challenges as well, so you'll still be able to access them. I'm trying to think of anything. Like, also just go through other CTF write-ups. Sometimes the write-ups will even supply the files that they were given, and then you can just go through the write-up and figure it out. Yeah, Tenchi?
You can also look at pwnable.kr and pwn.college. Those are great resources. Pwn.college is the binary exploitation course offered by the Arizona State University. They have like a whole thing that you can go through, and has like this whole level system, right, and has a full belt system. It's really good resource for getting into more advanced binary exploitation. Pwnable.kr is going to give you a bunch of binaries to pwn. Pretty cool. Do that. You should also, take a look at the contagion slides posted in the contagion channel. We just covered binary exploitation and reverse engineering for our group this Wednesday. So there's a whole slide on that.
Also 5 challenges you can check out on there.
Yes, exactly.
For those of you online, Tenchi was plugging his interest group. And also, if he has some resources for binary exploitation. So if you want any of those, reach out to him or ask in the Discord. Any other questions? Not seeing any. All right, well, I'm going to relinquish my role because I'm done.